plot it. I will make these thicker lines. So this is the plot. So these are the isothermal lines, and these red lines show us the flow of heat from 100 degrees Celsius to the zero this end, to the zero this end, and to this. Why did I show this? Is because we have already done this analytical solution for this two-dimensional rectangular plate. For example, if I take you to Incropera book, for example, I will take you to Incropera book here. Hello and welcome back. In today's video, what we are going to do is we are going to continue with another heat conduction problem. This time we'll take a two-dimensional steady state heat conduction problem with no heat generation, and it is also steady. So we might have studied this kind of geometry where we have a two rectangular plate where one edge is at say 100 degrees Celsius and other edges are at 0 degrees Celsius, and the general heat conduction equation, which is given by rho Cp dou T divided by dou T, is equal to del of K del dot T plus Q dot V. This is the heat generation, volume heat generation. This is the transient part, and we'll consider steady state and with no heat generation. So we will be left with del K del T equal to 0, and for constant thermophysical properties, K Laplace of T is equal to 0, and we will get Laplace of T is equal to 0. Now, if we see for a two-dimensional case, this becomes equal to dou T divided by dou x2 plus dou 2T divided by dou y2 is equal to 0. Now we have the solution for this kind of geometry, using these boundary conditions, four temperature boundary conditions. So let's move to the problem first. So what we have here is we have a rectangular copper plate in which top edge is at 100 degrees Celsius and remaining three edges are at 0 degrees Celsius. The length is 1 meter, height is 1 meter, and we want to find the temperature at the center of the plate. And for this center point, the coordinates will be 0.5 comma 0.5, which is 1 by 2 comma 1 by 2. So what we have to do is we have to find T at 1 by 2 comma 1 by 2 location using the solution, and we know the solution for this kind of problem is given by this equation here. Now this is the solution here, and we know this temperature varies sinusoidally with x, and this solution decays, temperature decays hyperbolic sinusoidally with y. So and also the solution is in the form of series. Since the solution decreases with y, which means we can choose first few terms to get the accurate solution. And the other thing that we have to remember here is we have this term over here where we have minus 1 to the power n plus 1. So when we put n is equal to 1, there is already 1, it become even, and minus negative power even is positive. So for odd it is positive, and for even, if we take n is equal to already 2, there is already 1, which is 3. So negative 1 to the power 3 will also again be negative 1. So negative 1, positive 1, it will become 0. So this solution will become 0 for all even n values. So we have to take only those. So our solution resides in the odd values of n only, and we will take first 5 terms in which two terms are even. So we'll neglect 2 and 4, and we'll take 1, 3 and 5, and we'll get accurate solution. We'll get a solution with very good accuracy. So taking n is equal to 1, n is equal to 3, and n is equal to 5. Now for n is equal to 1, we will solve this where we have all the terms known. N will be for n is equal to 1, n will be 1, x is at our location, our x is 1 by 2, y is 1 by 2, then w is width which is 1, l is the length which is 1. When we solve for n, when we solve these terms for n is equal to 1 and given values, we'll get, for n is equal to 1, we will get this the combination of these terms as 0.398. You can check this. I don't want waste time in this analytical solution. I want to move quickly to the COMSOL solution. For n is equal to 3, this comes out to be this, and for n is equal to 5, this comes out to be this. Then we have to sum up these terms, that the summing the contribution, this is negative, so that's why it's negative here. So we sum up the three terms, then we multiply it with the prefactor 2 t naught by pi. T naught is this 100 degrees Celsius. So what we'll do is, here is we uh, we multiply with the prefactor, and that prefactor is here multiplying by the prefactor, which is 2 t naught by pi. T naught is 100, so 2 into 100 is 200 divided by pi into this summed up term, and we will get approximately 25 degrees Celsius, the temperature at the mid center from the analytical solution. Now we'll solve the same problem using the COMSOL, and we'll compare it with that solution, whether it comes out to be 25 or something else. Now we'll open the model wizard and start with 2D. Then we'll go to heat transfer in solids and edit. And then we will go to physics and add stationary for our steady state. Now units already in meter, so we will we'll create the geometry rectangle. Now by default width is 1 meter, height is 1 meter, which according to our problem, and we will also add a point at the center at which we have to evaluate the temperature. So the center point is 0.5x and y is also 0.5. We will build the geometry. So this is our rectangle with this. So we'll close this geometry part. Then we will go to materials. We'll add material, which actually is not needed for steady state case because k gets cancelled out. And final temperature only depends on the boundary conditions. So still we added it. Then we'll go to heat transfer section, and this is solid, we have nothing to do with this. Then initial condition, let us keep initially whole thing at 0 degrees Celsius, since these three edges are initially 0 degrees Celsius. Then we'll add the boundary condition, so we'll add temperature, add this, and add this. Let us assign temperature of 0 degrees Celsius. Then we will add another boundary condition, and this time we will assign it 100 degrees Celsius, which is 393 Kelvin. Assign it to the top. We'll check. First temperature boundary condition is 273, which is 0 for three edges, and this is 393, 370. Let me check it again. So we have 273, which is 0 clearly, and we have 373 Kelvin, so which is 100 degrees Celsius. So closing the boundary conditions, then we'll mesh it, automatic meshing. Then we'll go to stationary and compute the value. It will solve this equation for all of these cells for us. Then first of all, what we'll do is we will, first of all, I will change this to rainbow because I like this, and I will change temperature to degree Celsius. Now first of all, let us calculate that value. We'll go to derived values. We have to evaluate the value at points. We'll choose that point, and then we will choose we will tell it to calculate it at in degrees Celsius. So we'll evaluate. So you can see our temperature comes out to be 20 degrees Celsius exactly, which matches our value. Which matches our value. I want to show something else as well. So I want to plot this. So I will choose 2D plot, and inside the 2D plot I will choose contour, and for the contour I will choose number of lines 10, level is 10, and I will plot this. So this is the isothermal lines. Along these the temperature will stay constant, and I also want to select a streamline, and number of line is 10, and I want to apply it to all the four boundaries. Basically what I want to calculate is how heat flows from 100 to these boundaries. So I want to choose type, I want to show arrows, and I want to choose the color red, and I want to plot it. I will make these thicker lines. So this is the plot. So these are the isothermal lines, and these red lines show us the flow of heat from 100 degrees Celsius to the zero this end, to the zero this end, and to this. Why did I show this? Is because we have already done this analytical solution for this two-dimensional rectangular plate. For example, if I take you to Incropera book, for example, I will take you to Incropera book here, and I can show you this is the solution that we solved, and so this is theta here instead of t, because this is non-dimensional form, and this is the solution, visual solution that they have given, which is exactly these are isothermals, and this is the heat flow arrows, which exactly matches our solution that we again can confirm here. So that was the problem that you did in undergraduate or postgraduate course, by solving general heat conduction equation analytically for this particular kind of geometry and boundary condition. And we solved the same in COMSOL using numerical solution, and we got exactly the same visual solution. That will be all for today's video. Thank you.